Hallo. Dus ik heb een doodle gemaakt voor de les. En er is iemand die kan vandaag niet om deze tijd. Dat is de reden waarom ik de doodle heb gemaakt. Dat mag geen probleem zijn. En de vraag is, dus vrijdag was een goed moment van 10 tot 11:15. Maar daarna was het niet meer goed. Er was er één iemand die niet kon. Een beetje de vraag hoe we het best doen. Ik heb vrijdag eigenlijk normaal niet graag, begin ik niet graag om 8:30 uur, maar dat zou kunnen. Hè. Dat is voor mij geen probleem. Dus dat is ook een optie. Dus maar we bespreken het best dan met de anderen.
Ik had ook 2 doodles gekregen, dus ik moet het zo'n beetje opsplitsen.
We zijn hier flexibel. We hebben hier 5 studenten. Dat betekent, eigenlijk mag dat geen echt probleem zijn. Ik weet niet hoeveel studenten in een andere groep bij jou zitten.
6.
Dus moet er wel een oplossing voor bestaan, want wie weet. In ieder geval hoop ik niet een student te verliezen, daardoor het overlap is weer anders. Ja, en vandaag is alleen overzicht en introductie, dus easy going. Maar zoals je ziet, is er wel een soort maar dat is het 1 lesuur. Dus ik geef gewoon deze overzicht. Voordracht die heb ik 2 weken geleden in Wien gehouden. Dan weten jullie wat zeg maar achter die titel zit. En dan gaan we daarmee verder. En wat zeg maar, de woordkennis betreft, dan kan het gewoon volgen zonder veel te weten. Dat is een soort mengeling van discrete wiskunde en logica. Dus logica, de bacheloropleiding is meer dan voldoende voor dat vak. En discrete wiskunde 1. Zo. Maar goed. 1 minuutjes. Ik maak ook lesopnames met Zoom. Goed, je moet kijken hoe het werkt, omdat Gent heeft nu de Zoom-licentie afgeschaft. En ik heb mijn eigen Zoom-licentie, maar dat is allemaal lastig. Hallo.
Hallo.
nog een andere vraag. Dus het vakje is aangekondigd in het Nederlands. Het kan zijn dat er nog externe studenten komen. In dit geval, de vraag is dan of er een probleem is als ik overschakel naar het Engels. Hallo.
Zou goed zijn.
Wat?
Voor mij zou het goed zijn.
Ja, het is geen taal, dus het juiste gebruik van het Engels speelt hier geen rol. Als het maar begrijpelijk is. Ja, in totaal zijn er 5 studenten ingeschreven. So in total there are 5 students. Plus some PhD students. Ik think I made an announcement on before, right? That we start today.
Yeah, what I made it, it's parallel to a different logic course. Maybe that's why. Maybe people went to the other one.
Ah, the other one is maybe is compatibility.
I think this one with Barcade.
Waarheid, modellering van de waarheid. Oké. Ja. Oké. Dus wachten nog 5 minuutjes en dan begin ik gewoon. Nu, de mensen die vandaag niet binnen zijn, daar was het geen probleem. Omdat ik heb dit doel opgemaakt ook voor voor vrijdag. Maar so what option would be Friday from 10? Or was it 10:15 was fine, but 10 to 11:15 was fine. Then 11:30 to quarter before 1 was not okay. Hello. So 2 things will happen today. First, I was discussing whether we can do the course in English because we have some external students. Hope this is fine. Second is we have to find a time where everybody can participate. And there was at least one student who said there's an overlap with another lecture. So maybe we can fix this first. So there was Friday. And it was fine on 10. 11:50. What's about, well, it's an early moment, but there was also the time from 11:30 to 12:45, but there was one student indicating that he cannot participate. See, he's not in, I guess.
Probably it was
Yeah, was it a serious issue or?
Yeah, not that serious.
What? Not that serious. Because there are 2 issues. We could move to this one, or then we have to start at 8:30. Means you have to wake up early, right? So I would prefer this one.
Do we need 2 hours or just 1?
2 hours. So that per week we have at least 2 hours, and at some moment we have student presentations and we need another hour, but this is somehow flexible. But to give it a start, I would suggest to use those 2 hours then. Nobody has something against this. So what's going to happen is this week I will start slowly. I will give my lecture today, and I will continue on Friday, just this time. But we are now in the master, so no fixed schedule. Everything is flexible, so don't worry. Yeah, that's one. The second one was I want to give the lecture in English. I will make Zoom recordings, which I will put on the Fora site afterwards. And yeah, as you know it, but the problem for me is now that Zoom is no longer supported by the university, so a bit of a hassle to do so, but anyway. Okay, now logic 2. Copy the selector, what does this mean, right? This means selected topics in logic. And what I will do is I will give an introduction into my research. And today I will give a sort of overview. And the overview comes with a seminar presentation which I gave some weeks before. And that was intended for a general audience, so don't worry that much. So what you will learn today is basically what I want to speak about. Well, organize this. So today the talk will be of expository nature, and it is addressed to general audience, and we will give some simple examples. But I put the slides already on before. No need to copy whatever you see here. There's a lot of different topics, several fairy tales, and I will somehow highlight some applications of mathematics within logic. The project itself is open-ended, so this means there's a very active research, and some problems are not yet finished, and so everybody who is interested in this can join in. Now, this talk which I gave had the title Phase Transitions for Gödel Incompleteness. Now, what is a phase transition? Now, everybody knows what phase transition is from real life. So if we have water, below 0 degrees, we have ice. From 0 degrees Celsius to 100 degrees, we have fluid, and otherwise we have steam. Now, what is interesting here is the specific points, 0 degrees and 100 degrees. There's a threshold point for a phase transition. Now the question is whether there is something similar in logic. It's not so clear. And if there are phase transitions, are there continuous phase transitions, or are there discontinuous phase transitions with sharp jumps? The question is which methods can be used, and can methods from physics be used to deal with this? Yeah, so the outline of this talk, so this is a talk which I gave in Vienna. So I gave some sort of historical introduction, and at some moment I start with these phase transitions, where you would will be largely already known. You know what piano arithmetic is. But anyway, I will start with what is piano arithmetic. It's a recap of the bachelor course. Piano arithmetic is a formal system which was intended to describe the behavior of the natural numbers. We have symbols for zero and successor, and then for addition and multiplication. You have the usual laws for these symbols, and you have the scheme of complete induction for formulas, which might be complicated. And PA is good for developing discrete mathematics. Now we know already the aim of piano arithmetic was to show, to describe the natural numbers up to isomorphism. But we know from logic by compactness that not every countable model of PA is isomorphic with standard natural numbers. Now we have the inconsistency naive set theory, which we know already from the Russell paradox. So contains this idea of forming sets by comprehension, and Russell wrote down the Russell class, and he could show that if you have unrestricted comprehension, then we have a contradiction. Then we have possible way outs to replace comprehension by separation and replacement. Actually, there's another course in the master education, namely set theory, Wisconsin Luca 3, set logic 2, where we study the axiom systems for Samuel Frenkel. We will see this in more detail. And as an answer to these inconsistencies of found in set theory and Fregel's Grundgesetze der Arithmetik, Hilbert, it's the idea of safeguarding mathematics by a program, Hilbert's program. And the idea was to come with a theory which is called proof theory. So the idea was to formalize all of mathematics, and then after the formalization, you show that what you have formalized is free of contradictions. And later Gödel showed that this is not realizable. So first question turned into mathematics: is every assertion true in the standard model already provable in PA? The answer is no. It's the first incompleteness theorem of Gödel. And the second one is consistency of a simple system like PA provable by finitary means. Finitary means would include the things being proven in PA. Yeah, so. And the second incompleteness theorem says, oh, the answer to this is no. So don't worry, I'm just giving a survey today, so cannot miss much. Oops. Now we come to what is called Gödel, trace transitions for Gödel incompleteness. So we have seen, Gödel showed there exists an assertion A in the language of PA such that A is true and PA does not prove A. Now, this is a very simplified version of Gödel's first theorem. Now, the question is, what can we say about such A? And what we do is we consider A with parameters. We make A depending on a parameter H. H could either be a number or it could be a function. And let's say H is a function. Then the idea is what? The idea is to have the situation if H is quickly growing, and we have the realm of unprovability, and if H is slowly growing, then we have the realm of probability. And if this is going to happen, then the magical question is, where is the transition? Now, this is basically the transition from low complexity to large complexity. And of course, such a diagram only makes sense when this property of being unprovable also is monotone. So say when something is unprovable and you go beyond this borderline, it should stay unprovable. Okay, now we come to what is called ordinals. The ordinals will be treated also in the course on set theory, but I gave this talk in Vienna to a general audience. So ordinals come the process of counting. We start with finite numbers, 0, 1, 2, 3. Then omega is the first limit, and then you continue with counting, and omega plus omega is the second limit point. And then you continue with counting. And in our course, basically, we are only interested in a specific segment of ordinals, which can be described by number theoretic functions. And the number theoretic functions under eventual domination. This goes back to mathematician Hardy. Around 1900, he has written a book, small booklet, about orders of infinity, and we are considering a subclass of the Hardy class. So what are these functions? Well, they are easy. So the constant zero function is in the class. And if you have two functions g and h in E, then we consider the following function, namely m moves to m to the g of m, so the exponential with base m, exponent is g of m, plus h of m. So we close the function class under exponentiation and addition. And then we order these functions, these unary functions, by eventual domination, meaning g is less than h if there's a k, such that if the inputs m are bigger than k, then g of m is smaller than h of m. And then it turns out that this ordering on the functions is a well ordering. And it's difficult to prove. Well, not so difficult, but it's also not so easy to prove. So one can show that the function class E with the smaller relation is linear order. That is sort of elementary to prove. But you can also show there is no strictly descending sequence of elements in E. That's the well orders. Okay, and now how can we model these elements of E with natural numbers? You will just the constant zero function corresponds to the number 0. Constant function value 1 corresponds to number 1. The identity function corresponds to the first limit element. Identity plus 1 is the successor of the first limit element. Identity plus identity corresponds to the second limit point. And now we write omega to the f for the exponential function. Function m goes to m to the f of m. And then the theorem is that every function in E can be written in a unique way as the sum of exponentials, where the exponents are weakly decreasing. It's a Cantor normal forms theorem, which works in general for ordinals, but in particular also for the elements in E. And if we have two elements in E, there's an effective procedure to describe when is one function smaller than the other function. And this is a sort of recursive procedure. You have a term representation for alpha, you have a term representation for beta. You write them in these normal forms. And then there's a property how to compare the exponents. So this is just alpha and beta have these representations. And then alpha less than beta, if and only if two options, either alpha is a strict subsequence of beta. So alpha is smaller than beta, the length of alpha is smaller than the length of beta, and all the coefficients are the same. Or the other option is alpha is not a strict subsequence of beta, then alpha and beta are compared lexicographically. Now what you see here is the comparison is done in a recursive way. If you have descriptions for alpha and beta, the comparison of alpha and beta depends on the components of alpha and beta, and therefore it's a recursive procedure to compare alpha and beta. And therefore we can move E and the Lassaigne relation into the natural numbers, of course, just by countability. But the ordering can be defined even in the language of arithmetic. So we assume that E is order isomorphic to the natural numbers with the Lassaigne relation. The induction up to alpha is now the scheme which I've written down over here. So what we see on the left is the premise of transfinite induction. So we assume that we can prove phi of x by assuming that phi of y is true for all y less than x. And if this holds for all x, then we have that for all x smaller than alpha phi of x. And the general So this is induction up to alpha. And the general induction is to have induction for all elements. If you have premise of transfer induction, we have for all x, phi of x. Now we will not see in the lecture, but it will be proved in the lecture on proof theory. Johannes Arithmetic does prove induction up to alpha for any alpha in E, but it does not prove the full induction. So in this sense, if you have this example, we have a sort of phase transition, namely we have probability for alpha in E, but if we go through the whole set E, PA does not prove the full induction. And this is the first example of a phase transition for Gödel incompleteness, but that's not the one we will see in the lecture. And what else can we say? Well, Gödel showed that PA does not prove the consistency of the Peano axioms. So there's something more needed. And the small ingredient extra is the induction over E. This scheme full transfer induction up to epsilon 0 of induction over E. PA plus I proves consistency of PA. Now, can forget about this. You just go to finite combinatorics. And I don't know whether you have ever seen the Ackermann function. The Ackermann function is an example of a function which is famous in computer science. It's also famous for having large function values. So what is a big number? A big number is, you write such a number on the board, it's a big number, but it could also be that the value is big. And the Ackermann function is designed to produce big numbers. How can you produce big numbers? Well, A0 of n is a successor function. It's not spectacular. If you put in 5, the Ackermann function, A0 of 5 is 6. So small number moves to small number. But the point is what? We have A0 of n is n plus 1. Now, what is A1 of n? A1 of n is A0, and then n times iterated applied to n. Now we have to iterate function application, so this is basically 2 times n. So if you iterate successor n times, we get doubling function. Okay. But now the point is, the next step is we consider A2 of n. It's A1, n times iterated applies to n. So it's 2n, 2 times 2n, 2 times 2 times 2. So it's basically 2 to the n times n. So it starts growing. The next one is A3 of n. This is A2. N of n, and then you see tower function. Once you have the tower function and iterate further, you see you get big numbers, right? And if you implement this function on your computer, you can try to evaluate what is A10 of 10. And the only thing what is going to happen is, whatever you do, you will get a stack overflow. You cannot print this number because this number is bigger than the number of atoms in the universe. Now this is much too big. A5 of 5 is even big enough, right? Maybe A4 of 4 is even big enough. So you see, this is a typical way of generating big numbers. In some sense, there's a description in logic functions called the class of primitive recursive functions. It's a class of functions which you can define by a simple set of starting functions, you close on a composition, and then you have a certain scheme of recursion. All these functions, A0, A1, up to AD, they are all primitive recursive. They are used by finite application of iteration schemes. But then there's finally the diagonal function AN of n. So A of n is a n of n. And this is growing so quickly that you cannot describe it by a finite iteration of recursions. So that's a famous example for a function which is not primitive recursive. Now, what we do in our lecture, we will study phase transitions for this function A. This is magical. Magical in the sense we are dealing with large complexities. And now the first thing is, how can we look at a phase transition for the function A? Because phase transition needs something to vary, phase an order parameter. Well, the question is, where can we introduce an order parameter? And it's going to happen over here. So we have A depending on H, and the number of iteration is no longer n, but is H of n iterations. And for the rest, AH is then the diagonal function. Now, what do we know? Well, if H is the identity function, then we get the function above from above. And we know the diagonal function is quickly growing. It explodes whatsoever. But when H is a constant function, right? When you have only a fixed number of iterations, then everything is under control. Then the resulting function A index H is primitive recursive. So it will be bounded by the Tower function. In this sense, A index H for H constant function will be a case of low complexity. Well, for usual mathematics, it's still large complexity. But in our course, we consider these Tower functions as having low complexity. Now the question is, here is it's a constant function, here is identity function. Where's the jump? Where does this function index H become, where's the transition? And it's a magical question, and it's non-trivial to answer this. Now, the answer will be the following. If you have a root function, if h of n is, let's say, the square root of n or third root of n, then A index H is not primitive recursive, so it grows enormously. And if h of n is a log function rounded up to a natural number, it's a binary length function or something like this, then A index H is primitive recursive. Aha, so log function, primitive recursive, square root function, non-primitive recursive. And then you can ask, can we do better? And in the whole lecture, we will learn how we can do better. So next result is the following. So if you have a function growing, weakly increasing and unbounded, then we can define the functional inverse function. So if h is such a function, then we can consider the function h to the minus 1. It's not 1 divided by h. It is a functional inverse. So it looks for the least m, such that h of m is at least as big as n. Now, what's the point here? If you have an exponential function, the inverse function is a logarithm function. This means if you have double exponential function, then the inverse function is log. So if the starting function is very quickly growing, the function inverse is very slowly growing. And that is what we are looking for. So what we are doing is take not the Ackermann function itself, but the functional inverse. Now, if you can implement this function easily on your computer, and you say put in constant 10 or so, it will always be an upper bound for the inverse Ackermann function on your computer. But in principle, the functional inverse function is also unbounded, but very slowly going. But there's no real bound on this. And then it turns out if h of n is the root of n, now the root, the exponent is 1 divided by A inverse of n, then A of h is not primitive recursive. And if h of n we replace here the inverse Ackermann function by a fixed branch of the Ackermann function, and then the result is primitive recursive. So that's a rather fine result, and just amazing that you can squeeze out structure out of the standard Ackermann function. And the proof idea is basically, if you have this function and you plug in primitive recursive functions, you never get any speed. The Ackermann function, the inverse Ackermann function basically works as a black hole for primitive recursive functions. So whatever you squeeze in, it never starts growing. Well, morally. Next thing is we can consider Ackermann function. Well, we start here with the successor function. We can also start with another function. Let's say 2 times n, or n squared, or 2 to the n, whatsoever. So we have an Ackermann function depending on g, and g is the starting function. And then we do the same as before. We iterate the start function. So agh, index d plus 1, is we take agh and iterate h of n many times, apply to n. And then we take the general function. And then you have a rather general question, given g, how can we modify h to generate a non-primitive recursive function? And well, this looks like a mission impossible, because there's no condition on g. Well, of course, we assume that somehow g is strictly increasing and at least as big as the successor function. These are some natural conditions, because if g is identity function, iterates identity function, we always get the identity function. That's not what we are looking for. But in general, this looks like a problem which is not beyond reach, because no structure is known. The surprising thing is we can solve this. So what we do is g prime of n is the iterate of g. So we take function g. So g prime of n is, we take function g, iterated n many times, and apply the result to n. So it gets speed. And now the result will be, if you take the function inverse of g, applied to n, you take the Ackermannian inverse root of it, then this function is not primitive recursive, and we take the same term and replace Ackermann inverse by branch of Ackermann inverse, and then we get primitive recursive functions. And this has lots of applications, and well, it's already the first result of a phase transition. Actually, it's a phase transition in the sense you have a sort of multi-dimensional phase transition. So you have here the situation where you virize a function parameter g along this axis over here, and you move these diagrams, and somehow the slope goes more and more downwards the higher you go with function g. Okay, but we are giving an overview. So next story is the Gustin sequence. Gustin sequence is a canonical example for the first result by Gödel. Now, how does this work? Well, it's number theory. So what we do is, first we define what is the normal form of a natural number. So normal form works with the number k. So we take normal form with respect to base k. K is the base of an exponential function. So every positive integer m can be written uniquely as m is equal to k to the r times p plus q, where m sits in between k to the r and k to the r plus 1. So this is sandwiching. And p is smaller than k, and q is smaller than k to the r. That's elementary number theory, discrete mathematics 1, I would say. Hopefully. Anyway, now comes the base change operation. The base change operation works as follows. So we replace k by k plus 1 in the base k representation. So when we have 0, there's nothing to be replaced. 0 of k is 0. And if m is k to the r times p plus q, then m, where we replace k by k plus 1, is k is replaced by k plus 1. So it's k plus 1 to the, and then in the exponent we replace k by k plus 1 times p. P is smaller than k, nothing to be replaced. And we have q of k. So in q we also do the base change. So what's going to happen? So if we have, let's say, 2 to the 2 plus 2, and we replace base 2, it will become 3 to the 3 plus 3. So what does this mean? Numbers become bigger, bigger, and bigger, and bigger. So there's a clear explosion. And now we form a sequence, the Goodsin sequence. So we start with our favorite number m. And m0 in the sequence is m. And if ml is bigger than 0, then ml plus 1 is what? We take ml, we write ml with respect to base 2 plus l. And then we replace 2 plus l by 2 plus l plus 1, making the number bigger. And then we subtract the 1. So if you see it over here, you clearly see a divergent sequence. You can check on your computer, it's diverging, but we use our example, right? So m0 is m, m1 is 3 to the 3, minus 1 is this number. The next one is 4 to the 4 plus 1. The next one is 5 to the 5. Now we write down the statement G. For every number m, there exists an L such that ml hits 0. So this looks like a wrong statement. Of course, why I'm showing this, because it's not a wrong statement, because it's a true statement. We can show G is surprisingly true, and it's not provably so in kernel arithmetic. And in our lecture, we will see a proof of this. This example is even mentioned in the book by Penrose on physics and so on. Somehow, it is good for popularizing mathematics. You can easily explain these Goodsin sequences to a non-logician because there's no need to explain what the axioms of kernel arithmetic are and whatsoever. Now, what is the phase transition here? Well, when we see this definition of the Goodsin sequences, there is nothing to be modified. But what we do is we do what we ever do. We introduce a parameter. And the whole lecture is about taking assertions, introducing a parameter, and then look what's going to happen about it. So let us introduce a function parameter h for the Goodsin principle G. H is non-decreasing. Now what we do is, in the Goodsin process, we develop not with respect to base 2 plus k, but with respect to base 2 plus h of k. And we replace in our Goodsin process, oh, this k would be an h, but for the rest it's fine. We replace 2 plus h of k by 2 plus h of k plus 1. So this is a definition of the Goodsin sequences. So instead of using the identity function for the base change, we are using function h. And then we define the Goodsin process with respect to function h. And then the statement is what? G of h is the termination assertion for Goodsin sequences with respect to function parameter h. then first of all, g of h is true for all functions h, which are non-decreasing. Now, if I have a fixed iterate of the log function, or fixed iterate of the binary log function, so it's log of log of log d many times, the PA is not able to prove it. Now, if you go to the inverse function, inverse function of the Tower function, which is very slow growing, then it becomes provable. So we have a phase transition between iterates of log and the inverse of the Tower function. Now, the inverse of the Tower function is already a function which converges on every computer. So in computer science, this is a famous function which shows up in many complexities. And this is considered as almost constant, but in theory, it's an unbounded function. Next one. So today I will just give example, right? And jump from one example to the next one, to the next one. Just making some advertisement. There comes now the famous result by Paris-Harrington, and it has to do with Ramsey theory. I don't know whether you've ever seen Ramsey theory. Ramsey theory is part of discrete mathematics, and it has to do with the slogan that complete chaos is impossible. Whenever you have a system of chaos, or so within every large enough system, you have some smaller system which is well organized. And that's basically the idea of Ramsey. So we identify a number R with a set of its predecessors. So R is a non-negative integer, and R is identified with a set of numbers from 0, 1 to R minus 1. So the canality of the set is just R. Now with X in brackets to the D, we denote the set of D element subsets of X. It's a bit of a complicated notion, but okay, anyway, but it's clear what it is. So we take the subsets of X, which have canality D. And the finite Ramsey theorem works as follows. Now, this is complicated. Why is it complicated? Because there are so many quantifiers involved. So what is the idea here? The idea is we start with three elements, D, C, and M. Now, D stands for dimension, C stands for the number of colors, and M is the lower bound for the canality of a certain set. So for this triple, for every triple, D, C, and M, there exists a number R. R is the Ramsey number. Saying if our system is as big as R, I find a nice subset of canality at least as big as M. So R is so big such that for all colorings, for all partitions, for all P, which are functions from the D subsets of R into a set of canality C. So that's somehow the situation of chaos. In that system of chaos, we find an H. H is a subset of R. This is identification from above, such that the D subsets of H are monochromatic for P. So all elements in H to the D get the same number, the same color given by P. That's called homogeneous or monochromatic set. And the set is not the empty set, because the empty set would fulfill this. But the canality of H is at least as big as M. So if R is big enough, and you have some coloring, then there will be a nice substructure of R, namely the H, the homogeneous set, such that all the element subsets of H get the same color. Now, that's the famous Ramsey theorem, the finitary version. And if you're doing discrete mathematics, you should know this, because many solutions, many problems in discrete mathematics can be solved by Ramsey theorem. I guess you have never seen it before, or did you? If not, I can cover this in the lecture. So anyway, Ramsey theorem is a true statement. That's already good. Moreover, it is provable in Peano-Smyttik. Why is this the case? Because Peano-Smyttik is able to deal with discrete mathematics. And moreover, the Ramsey function is bounded by simple function by an iterated tower of exponentials. So IDC of M is bounded by a tower of 2's of height d minus 1. In this exponent, we have constant times C times M. I don't know the constant yet, but anyway, it doesn't matter so much. Okay, now the problem here is for Ramsey's theorem, there is no phase transition. Now the problem is, how can we smuggle in the phase transition? Well, we have to modify the finite Ramsey theorem, and that's where Peres-Harrington come into play. They modified the finite Ramsey theorem. And what they did is they added a new component. The canality of the homogeneous set is not is at least as big as M, that was as before. And they also said canality of H is at least as big as the minimum of H. Well, it looks a bit mysterious, maybe even self-reflexive. Anyway, one can show that pH is a true statement, and Bernoulli's critique does not prove pH. So this means, oh, yeah, right. So this, first of all, we have a statement which is unprovable. That's the first one we need for phase transition, some statement which has large complexity. Now the question is, can we smuggle in parameter H? Now the idea is we smuggle in H where the minimum of H is waiting. Yeah, here you see it. Peres-Harrington with parameter function H, the same as before, but here we see the homogeneous set H has canality at least as big as H of the minimum of H. It's not canality of H is at least as big as the minimum of H, but a function of the minimum of H. And then we see easily Peres-Harrington for H is always true. If you have log star, PA does prove it. And if D is fixed, and we consider a fixed iterate of a logarithm, then PA does not prove it. Aha, again, a nice phase transition. And there are lots of variations of this, which we'll see all in the lecture. There's a regressive Ramsey theorem. There's also canonical Ramsey theorem. Anyway, lots of things. What we see here is log star and log D. And we have seen this before. We have seen this in the example of Gaussian's theorem. It was the same phase transition. And that's a bit like in physics. You have many different situations, but somehow the thresholds are quite often the same for whatever reason, just as by nature. And here comes the proof. And the proof is absolutely mysterious because it comes out of the blue. How is it possible to prove pH, Peres-Harrington, with respect to log star? This looks like mission impossible because we have to deal with the condition that canality of H has to be at least as big as log star of the minimum of H. We have not the slightest idea how to deal with the minimum of H. Now comes the proof. So what we do is we start with three numbers, M, D, and C, and then we say the number R for Peres-Harrington is the finite Ramsey number. Now this looks a bit fishy because the finite Ramsey number has no condition regarding the minimum of H. So we have the finite Ramsey number with dimension, let's say D times 2 or whatever, doesn't matter that much. Basically, it's a finite Ramsey number with respect to D, C, and M, maybe a bit enlarged. And since the Ramsey number is obviously monotone in M, D, and C, we can take the maximum of M, D, and C and plug it over in. Okay, that will be a nice number. And Ramsey theorem is provable in PA. Now let partition P be given from R to the D to C. Actually, it should be D times 2, but anyway, typo. By Ramsey theorem, we find a homogeneous set such that P, when restricted to the 2D subsets of H gives constant number, and affinity of H is at least as big as 2M. That's also fine. Now comes the trick. The trick is one line. So we have to bound log star of minimum of H by scalarity of H. And how is this possible? Well, log star of minimum of H. Now we do what is absolutely impossible if you do analysis or whatsoever. We replace the minimum of H by the maximum. So that's the most trivial estimate you can come up with. But that's basically the explanation, right? So minimum of H is bounded by the maximum of H. And this sits in the set R. Now we use bound for finite Ramsey numbers. So it's a tower of twos. So it's log star of a tower of twos, let's say 2M. But then log star is the inverse function of the tower function. So we get the number 2M back. And it's bounded by continuity of H. So that's a magical proof, because the condition here comes out of nothing, so to say, and comes out of finite combinatorics. But this is quite typical for phase transitions. On the versions which are provable quite often come from discrete mathematics. And once you get the situation where you cannot do such a proof, then you have a chance of getting unprovability. Okay. Moreover, what we see that the threshold function is basically coming as a functional inverse of the bounding function coming from finite combinatorics. This is what we see over here. The log star function is the inverse of the finite Ramsey function. Okay, now we come back to the next one. We are counting ordinals. We count members of E. So the complexity of a term alpha is sum of exponentials. It's just the number of exponentials showing up in alpha. So the norm of alpha is n plus complexities, sum of complexity of what is in the exponents. And then for all D, the set of all alpha in D with bound norm is a finite number. By simple combinatorics is bounded by an exponential function. Now we consider the function C alpha of n, which is a number of beta less than alpha, such a number of beta is equal to n. Now by simple counting, C omega to the D is basically a polynomial. That's fine. Now the question is, what is C omega to the omega of n? So it's the first true exponential function. So do you have any guess what this number is? Maybe not. And if you have never seen it, it will be surprising. There's not this question on what is this number is not a simple answer. You even have problems in guessing how to calculate these numbers. So the first thing is what you could come up with is doing a sort of proof by induction, you estimate some exponential bound, but it's not going to work. So why it doesn't work? First of all, there is an explicit formula with equality for this, but the explicit formula for this would start here and would cover the whole board. So that's too complicated. So what we do is we consider approximate equal. So an is absolutely equal to bn. It's a ratio of an to bn converges to 1. Now, what comes here? First of all, comes the Euler number E. Then we have the circle number pi. If here square root of 2 divided by 3 times n divided by 4 times square root of 3 times n. Aha. So it is difficult to guess this right in the beginning, right? Yeah. So Aha. Here comes a solution. We look at classical work by Hardy and Ramanujan, and they already did the work for us. So that's good. And why is this the case? Because there's a bijection. One can show that this number is equal to the what is called partition number, the nth partition number. And then Hardy and Ramanujan calculated asymptotics for partition numbers. Aha. But it's a great result. And just now, has anybody any idea how to prove this? Maybe not. Now, the trick in discrete mathematics is what's called generating functions. You may have heard about this. This is proved by a technique called generating functions. Moreover, next one is what is C omega to the omega to the omega? Good question. Actually, it's even more difficult. So what we do is we consider not asymptotics for this one, but we take log of this function. And try to get asymptotics here. And what we get is the log of this counting function is pi squared over 6 times n divided by natural log d times iterated applied to n. Well, what is this? Rather surprising. But anyway, this can be proved by a number theory. So, now there's literature on this, and I put an article on Ufora by Petro Gradsky, and in this article you will find these calculations. We'll find it also elsewhere. Anyway, the question is, why did I show this? Right. For this, we come to Harvey Friedman, and he studied also independence results for Peano arithmetic. SWO stands for slowly well-orderedness of ordinals, function class E. So what does the statement mean? Well, we are speaking about sequences of ordinals, sequence of elements in E. And what we know is E is well-formed. There's no strictly decreasing sequence. So if you have given any sequence alpha I, there will be an index I such that alpha I is less than or equal to alpha I plus 1. Because this means it's not strictly decreasing. Now, this is a statement speaking about infinite sequences. The well-formedness is a second order property, but Peano arithmetic speaks about first order properties. First order properties means you have to speak about finite sequences. And Harvey Friedman was able to move these infinite sequences into a strong statement about finite sequences. Now, this is a statement. Given K, there's number M. M is big, so big, such that for all sequences of numbers, ordinal numbers, they will not be strictly decreasing. There will be an I such that alpha I is less than or equal to alpha I plus 1. Now, it does not work for all sequences of length M, but for all sequences of length M which are growth controlled. Namely, the control is the norm of alpha I is bounded by K plus I. And then this statement is a true statement, which is not provable in Peano arithmetic. Now, question is, of course, putting in K equal to 100, how big is M when K is equal to 100? Well, it's bigger than this number. So it will be a big number, but in the lecture we will learn how to deal with these numbers. We want to see phase transition here, and what can we do here? Well, we zoom in here for the I, and we replace I by h of I. Yeah.
What is that in?
What?
Alpha I? In the assertion of SWO.
Yeah.
N alpha I.
Yeah, this is a norm function, which I hopefully have over here. It's a norm function defined above. So the norm of alpha is counting the number of exponentials showing up in the representation of alpha. Now it looks a bit unnatural, but there's a sort of canonical understanding of it. Maybe I write it over here. So every ordinal alpha, so form omega to the alpha 1 plus omega to the alpha n. Alpha 1 is bigger than alpha 2, bigger than alpha n. But for every ordinal, we can associate the tree T alpha. T alpha is basically the associated tree to alpha 1, to alpha n. And we connect these trees as a root. And T of 0 is just the tree with one root. And what is the norm of alpha? Well, we take the tree, T alpha, and then we take the number of edges. It's the same as the number of points of nodes in T alpha -1. So then you have a sort of graphical interpretation of what the norm of alpha is. Anyway, now what is the phase transition? Well, as I said, we plug in the function h of I, and then we ask what is going to happen when we vary the growth rate parameter h. And then if we have log times log star, it's a provable. And if you have log times a fixed iterate of log, then it becomes unprovable. And now comes the explanation, the high-level explanation. So it is a strange result on counting functions, this weak asymptotics with pi square or 6 whatsoever. This function over here is basically the functional inverse of the counting function. So again, the finite combinatorics gives some hints where the threshold is waiting, and okay. And to prove this unprovability stuff, we apply some sort of renormalization operation and some squeezing down of threshold, like in physics. But anyway, you don't need to know physics for this course. And now we can modify the statement. You can replace the norm function by Gödel numberings whatsoever. And then at some moment we jump from additive number theory to multiplicative number theory. Can study this one. Next one. And actually, the next one is the one which brought me into this popular science magazine EOS. So phase transition for Kruskal's theorem. So for this, we come again back to a finite trees. Finite tree is a finite partial order such that T is a minimum, the root. Okay, here's the root. And if we have some node in T, and we go downstairs, these points are sitting on a line. They are linearly ordered. That's fine. Then if we have, let's say, nodes in a tree, there will be a notion of infimum of 2 points. And the point is it's the first point when you go downwards where these lines meet. So that's infimum of these 2 points. So for every S in T in tree T, there exists an infimum. And a one-to-one function T, one-to-one function E, going from one tree T into another tree T prime is called an embedding, an homomorphic embedding, if it's one-to-one injective, and preserving the notion of infima. And T, the embedding to T prime is not denoted by this statement. Okay, and then there's a famous result. And the famous result by Kruskal is if you have an infinite sequence of finite trees, then you will find two moments in time, I and j, such that I is smaller than j and ti is embeddable in tj. It's a bit like Ramsey theory. All sorts of chaotic situations, there is some moment of structure. And now, if you want to prove this, you will have problems. Because usual discrete mathematics does not suffice. Don't forget about what is written here. It's just very difficult to prove. You need some new techniques, but I will show it in my lecture. And Harvey Friedman got famous for proving that this theorem is not provable in what is called predicative analysis. So there's no way to prove this theorem in a set theory where sets can only be defined by referring to previously defined sets. Okay, here's Harvey again. It looks like Kruskal's, the miniaturization of Kruskal's theorem looks like the one for slowly well-orderedness, but it's slightly different. Now speaking about trees and not about ordinals. So if you have a tree T, the norm of T denotes the number of nodes in T. And FKT, Friedman's version of Kruskal's theorem, stands for every K, there's an M. M is so big that below M we find indices I and J such that Ti is embeddable into Tj. Now, when does this going to happen? Well, so for all K, there's an M. If the sequence is long enough and well behaved with respect to growth rate, so the number of nodes in Ti is bounded by K plus I, then there are I less than J such that Ti is embeddable in Tj. And then this is a true statement. And it's very difficult to prove that this is true. So it's not just doing some induction. You need basically the infinitary version with the infinite sequence of finite trees. And Peano's arithmetic does not prove this statement. Actually, even stronger theory don't prove this. Where's the phase transition? Well, as you might imagine, you replace here I by h of I. And okay, we have then fkt of h, this we just explained. And now what's going to happen is fkt of h is always true. If h is constant, then PA does prove it. If h is identity function, PA does not prove it. And the question is, where's the phase transition? In the literature, the first result was by Matuszek and Löwe, and they considered a log function. Logarithm function. It was a binary length function, binary logarithm with respect to base 2, maybe rounded to a natural number. And they showed if our function h is hr of I is r times binary log of I. If you are below 0.5, then we have probability, and if r is at least as big as 4, we have unprobability. Aha. And now the question is, well, so here we have 4, here's 0, here's 2, here's 1, here's 0.5, here's 3. Where is the threshold point? So who believes that this interval? If anybody believes that the phase transition point is in this interval, on this interval, in this interval. Yeah? Okay, you may have seen it before, but anyway, it's more or less impossible to guess. And So in 2000, I was visiting a professor in Japan, in Hiroshima, and he was rather busy. So basically, I was sitting for some time alone in my apartment. And what can you do when you're sitting alone? You're just doing some mathematics, right? And at that moment, I figured out where this threshold is located. Now the question is, how can you attack this problem? Well, you have no idea. So nowadays, what you would do is you would start with Google, right? Try some guesses. And this is what I basically did in 2000, but Google was not so well established at that moment. But I was using a search machine and I was looking for finite tree. This choice, right? And then I found something interesting. Namely, there was a web page by Stephen Finch on mathematical constants. There was a mathematical constant related to Kruskal's theorem, or to tree counting. And once I have seen the constant, I said, that's the one I need. Well, of course, wishful thinking. There's no guarantee that it's helpful, but it was helpful. So that's the number, C. It's over here. Well, now, see many digits, right? Is this a rational number? The answer is unknown. Could even be a transcendental number. But it's a number which you can calculate on a computer. You can calculate the digits on a computer. So the longer you calculate, the more digits you get. So in principle, you can calculate every digit. Enough power. But okay, now the question is how to find this number. First of all, the result is if R is less than or equal to C, then PA does prove this Friedman version of Kruskal's theorem. And if R is bigger than C, PA does not prove it. The next question is, what is C and how did I find it? Right? And I actually explained it already. So the first guess was using the internet. So I looked for finite tree and I found a tree constant. What is tree constant, which is 2.9557765. And C is 1 divided by a binary log of alpha. Now, did we learn something here? Not yet, right? So still not clear what these notions are. So next question is, what is alpha, right? Well, alpha comes by tree counting. So the mathematical explanation of alpha is the following. T of z is a generating function, which fulfills a certain law. T of z is z times exponential of sum of t of z to the I divided by I. The point here is not a recursive definition of t, but it's a sort of implicit functional equation. And one can show this has positive radius of convergence, a rho, and alpha is 1 over rho. Now it's even more confusing, but the point here is this description can be used to calculate the digits of alpha. Just by approximating these infinite series by finitary ones and using large enough polynomials whatsoever. Now, question is, what are these coefficients Tn? Well, first of all, Tn is the same as basically asymptotically equal to alpha to the n. So it's an exponential with base alpha. Okay. Now still the question, what is Tn, right? Now comes the answer. Tn is the number of trees having n nodes. So what do we learn by this? Counting trees is more difficult than you would expect. So whenever you have a problem of counting trees, be aware that it's non-trivial, right? You have basically an upper bound. Normally, if you count trees, you have 4 to the n. An upper bound, which always works, some induction on n. But you if you want to have precise information, it comes. Okay, and now this threshold function, which is coming up over there, finally is basically, it takes a function inverse of this function. So you have the number of n, this function n. It takes a function inverse, you get the threshold function for probability. So it's again this type of philosophy that you have, if you have information about your counting, about finite, about the discrete mathematics part, then you can guess somehow the threshold. And the digits of C have been calculated by some student in Germany. Okay, now this looks good, right? This is a rather strong result. There's one point where you have a sort of clear threshold between probability and unprobability. The question is, can we make it better? Can we refine this? The answer is yes. That is a magic, but it's rather involved. So as this constant C, and I consider is basically C plus epsilon I times final log of I, where epsilon of I converges to 0. Now what is this? This is what is considered to be a scaling window of a threshold function. And now, depending on the speed of epsilon I to 0, there will be this classification. But this is rather advanced. So what we do is, first of all, we extend the Ackermann function into the transfinite using these numbers in E. So we start as usual with the successor function. At successor stages, we iterate the previous function. At limit stages, we take, so if lambda is a limit, then lambda x converges to lambda, and we take the diagonal along this fundamental sequence. And finally, we take the diagonal function over all of E, where we have certain laws for lambda. Lambda x converges to lambda, where omega to the beta plus 1 of x is omega to the beta times x. And otherwise, lambda x is somehow naturally defined by some sort of continuity. And here I have the function h alpha of I is c plus, and here comes a function converging to 0. This is the epsilon of I times final log of I. Now parameterized with these alphas. And this is the final upshot. If alpha is an element in E, then PA proves this. And if alpha is going to the limit of E, then we get unprobability. Okay, well, this was the technical stuff. And now it's high time to switch topics, otherwise you get lost in the details. Now we come back to first year semester analysis. We have learned what is Bolzano-Weierstrass. Bolzano-Weierstrass is very simple. You have your unit interval. Here it is, 0, 1. And then you start with some sequence. And then you can find a subsequence which is convergent. And we know how to prove this, right? We divide this interval into two parts. You have an infinite sequence. In one of the two parts, infinitely many elements of the sequence will survive. Then you do another bisection to check again in which part of the interval, an infinite part of the sequence remains. And then you continue. Finally, you will find a limiting point, and you will extract a subsequence which is convergent. Okay, now the question is, what can we do with this? Another version of it is the monotone convergence theorem, which is even easier. And if a non-decreasing sequence, the unit interval is just the converging sequence. And that's all fine. Now we come to Harvey Friedman again, and what he did is we came up with a new version. So if you have an arbitrary function into the positive numbers, typical example would be 1 divided by I. If you have any infinite sequence of real numbers in the unit interval, then there exists a subsequence such that the distance between the largest of the three elements, there exists a subsequence K1, K2, blah, blah, such that for all I, we have three players, Ki, Ki plus 1, Ki plus 2. And if he takes the two biggest ones, takes the difference, and the difference bounded by f of k of I. And this is a true statement, which can be proved using the other version of Bolzano-Weierstrass. So basically, we pick a subsequence of the original sequence, which has a converging subsequence as a limit. And then once we have the limit, we can construct the Ki by some sort of recursion. It's easy matter. Now comes something funny, namely, what you also learned in calculus is the following. Namely, there's this threshold between convergence and diverging integrals. If you have what? Well, let log d be the default iteration of the log function. And then if you just consider this one here, 1 divided by x times log of x times log of x, blah, blah, blah. This integral is diverging. And if you replace last term to the 1 plus epsilon, this is converging. Now the question is, what has Harvey-Friedman's theorem to do with this type of theorem? And this is what we will learn in this lecture. So Harvey-Friedman showed the following. Namely, he took his Bolzano-Weierstrass theorem, he turned it into a first order statement for k. There's M, such that for all sequences of elements in the unit interval, there exists a subsequence of length k, such that if you take 3 consecutive elements in the subsequence, then the difference between the two bigger ones are bounded by 1 divided by index of the lowest one. And this should hold for all I less than k minus 2. Now the question is, how strong is this statement? Well, in general, we can replace 1 over ki squared by f of k of I. How to prove this? So Friedman's original proof was using compactness of this product space. Now, and if you have ever heard about topology, you know what a compact space is. And then the product of compact space is again compact. But here we have an infinite product, and that's a famous result by Tikhonov. And voila. But it's a bit of overkill. You can replace Tikhonov by some easy proof. Now, okay. Now we want to know what is the phase transition over here. And we come back to the classical Ackermann function. Now this is a slight version where in the successor stages I am a bit slower than over here, but not much slower. So basically the Ackermann function of d1 n is basically Ackermann function of d n many times applied to 1. But it has basically the same growth rate as the other one. But Harvey-Friedman showed if you have 1 over I squared, and then the least mk for his Bolzano-Weierstrass principle is at least as big as Ackermann of index k minus 8 of 64. Meaning if you plug in k equal to 13, then you have this number Ackermann of 564, and this is big. It's so big that you cannot calculate it on your computer. Now, by some brute force, you can also show that m of k is bounded from above by an Ackermann function. And if you do this proof, then you finally can get rid of your application of Tikhonov. It's just finite combinatorics. Okay, now the question is, Harvey, what happens if you modify the function f? You go down by 1 over ki squared. And so if you replace 1 divided by ki squared by 1 divided by ki to the 1 plus epsilon, you still get Ackermannian upper and lower bounds, not published. Okay, what about lower bounds? If f of I is log of I divided by I, then m of k for Friedmann's theorem is bounded from above by an exponential function. So it says low complexity. So you have some space. So you have log of I divided by I, low complexity. And if you have 1 divided by I to the 1 plus epsilon, large complexity. In between, there's this phase condition. Proof, easy exercise. So when you want to learn about this, you can just start, and it's basically as simple as the one which I showed for Paris-Harrington. You can give it a try, and if you don't succeed, don't worry, I will give it in the lecture. But this could be given to a first year's bachelor student. Maybe you don't believe me, but you need the keyword simple bisection argument. Bisection argument is, you've seen it over here with the infinite sequences. If you take this proof for infinite sequences into a proof for finite sequences, the proof will work for this complexity function. Okay, and now in 1999, Harvey was asking the question, how does this function m of k behave for f of I is equal to 1 over I, and f of I is 1 divided by I times log of I. And he just said he's not able to do so. And so the question is, do we get large complexities or do we get small complexities? And I was busy last year with answering this question. And I will basically sketch how I approach it. Well, what are you doing when you have such a problem? There's this famous book by Polya on how to prove mathematical results. If you can't do the original problem, you do a simpler problem. First, I did a simpler one, namely, I replaced Bolzano-Weierstrass by the monotone convergence principle. So I was looking at the Friedmann statement, but just monotone, really increasing sequences. I was first looking for the threshold for this problem, which is simpler. Okay, and then I showed if I take the function from Friedmann, 1 divided by I times log of I, then the least mk for Friedmann's monotone convergence principle is bounded from above by a double exponential function. That's already good. And of course, if 1 divided by I is bounded from above by an exponential function, so it's low complexity. And if I have the function 1 divided by I times log of I to the 1 plus epsilon, I get large complexities. Now, the integral over this function is diverging. The integral over this function is converging. But funnily, converging integrals come with large complexity, and diverging integrals come with low complexity. But this is basically what is going to happen. Okay, then I went further. So I studied now the more deep iterations, 1 divided by I times log of I times log of I. And then I got an upper bound by a d plus 1 times iterated exponential function. Okay, that's good. Now, if fd of I is what? I take my function AD, function inverse, very slow, take the difference. Then it turns out that what? Then the result from above is still true, namely m of k is still bounded by a primitive recursive function. So that's very good. I get a strong result on lower bounds. And for upper bounds, I took the function from there. Last term is replaced by log beta iterated applied to I to the 1 plus epsilon. Then I get large complexities. So you see in this theorem on integrals, converging integrals, large complexity, diverging integrals, small complexity. And now what happened is I was not able to continue. So I was solving the problem for monotone convergence, but that was not the original question, right? I had a nice result, but I was answering the wrong questions. So I spent another year to get insight on the full result. Well, in logic, there is a theory what is called Weierauch degrees, and then there is a difference between Bolzano-Weierstrass and monotone convergence. So I tried for a long time to show that for 1 divided by I, log of I wanted to get Ackermannian lower bounds for the complexities. I tried hard, tried and tried and tried, never succeeded. But I had some external motivation to show this. But that's the bad thing in mathematical research. You try to prove something, you have some idea why it should hold. The only problem is I was trying to prove the wrong theorem. So you can try whatever you do, you will not succeed. And at some moment, try to prove the negation of the statement which I want to prove. So for 6 months, I tried to build long sequences with fractal structures whatsoever for this non-monotone Bolzano-Weierstrass. And I never succeeded. I had some ideas what to do, but no success. So I gave also this talk in China. So I said for a long time, as long as the Chinese won over here. Okay, well, now comes the solution. The solution is that if I have the situation of diverging integrals, then I have low complexity. That was, for me, a complete surprise. And actually, the proof is not that difficult. To my surprise. Of course, I tried hard to prove the wrong theorem. I never succeeded. Then I tried to prove the opposite, and suddenly it came out. What is going to happen? If I have differences of the Ackermann function, and function inverse of branches of the Ackermann function, I get these primitive recursive lower bounds. That's fine. And if I have this function, I get Ackermannian lower bounds. So I have here primitive recursive upper bounds. Okay. Next question is interesting spin-off, which I find interesting. What is, so you see all these functions over there, and these are discrete functions. Now we can think about canonical extensions to smooth functions. So what is the difference between these two function values? Well, when you see the difference like this, f of I minus f of I minus 1, you know, you have this intermediate value theorem for derivatives. You can ask what is the derivative of the inverse Ackermann function? Good question. A bit of an esoteric question, but the answer will come out. So it's the following. We come back to our original function A. It's the same as this f. And here we form certain products. So we start with 1 over x, and then we iterate these terms which we see in the theorem on converging divergent integrals by some recursive procedure, which is now too difficult to explain. But first of all, if we look at theorem by Abel, we can show basically the integral of the infinite sum over the d index d of I is diverging. If we add a new factor at the end with 1 plus epsilon, it will become converging. And basically, my idea is that this difference, or the derivative of inverse Ackermann, will be of this form, for whatever reason. Now again, it takes the same function as before. Now, what is the phase transition for Friedmann? Yeah, well, he takes these complicated expressions, and then we make the index d depending on x, so it's d star. And if d star is a function which is weakly increasing, then basically this function generates Ackermannian growth if and only if d star is unbounded. And Ackermannian growth is the same as unprovable in the system with one quantifier induction. Okay. And then there's a new one from Harvey, Weierstrass theorem for full piano arithmetic that we don't know. I'm working on this, and so, but it might be difficult, and yeah. But that's basically the description. And now something magical occurs. Really magical. So what happened is I gave this talk in Vienna. And there were some people in the audience from a different field in logic, from model theory, Matthias Aschenbrenner. And he's an expert on what is called serial numbers. Have you ever heard about serial numbers? Well, you can Google for it. It's a magical field. Conway has written a book on this, famous Conway. And there's also a field which is called quant series. Certain formal power series in variable x using normal operations and x and log, but transfer net, something like this. And Aschenbrenner was pointing out to me that there is a version of iterating a log function, transfer net alpha, and the version is basically having this property. Now, this is not really mathematics. It's formal power series whatsoever, but they are somehow well defined. And it seems that those terms have to do with the Friedmann result. But this is basic stuff which is 2 weeks old, and I don't know yet how you can really make mathematics out of this. There is a French mathematician, Jean Icard, famous one, ICM speaker. And he knows how to move these formal expressions into real functions. Say. And, now we are discussing what you can do with this. So that's a bit open-ended. I don't know whether I'm able to describe this in this lecture, but that's really actual research going on. So we will cover some of this in this lecture, but only the stuff which I understand by myself. Okay, that's basically enough for today. And do you have to recall everything? No, the answer is no. This is just a survey. So I'm just indicating something. Today we have seen lots of statements about provability and unprovability. We don't need this for our lecture. What I will do is I will use a sort of alternative description. The alternative description is just in terms of fast growingness versus slow growingness. And this is can be formalized just by discrete mathematics. And we will learn to distinguish large complexities from small complexities. And that's basically what we are doing. And you start with elementary stuff. Elementary stuff is, I will start with Ramsey's theorem. Ramsey's theorem not for dimension D, but for dimension 2. I will study Perez-Sarington theorem for dimension 2. And everything will be easygoing, elementary. And what you will learn is that many small steps will add up to something big. And, but the whole lecture is about collection of all of these results, one after the other. And today was a sort of global picture. And on Friday, I will start with specific mathematics, say, but not as advanced as this. This was a sort of overview talk. And don't worry if you are lost somehow, it doesn't matter. Friday, I will start at the bottom level, step by step, and you will be able to follow every step. Okay, that's basically the idea. Enough for today. And we will see each other Friday morning. 2 options, either here or in Hjarðarsaal 3.2. Well, or elsewhere, depending on. Now, let me just ask: was it possible to follow? Or yeah, and well, I hope that. Well, I do not want to lose students, so to say. So, if you have something to say or want to say where I can improve, let me just know. And I'm willing to also to adjust some of the lecture to the need of the students, or whatever you want to see. And but now, before I continue, I will first stop my Zoom.